Before proceeding to our next talk, can I please ask some of those standing near the walls to please take up some of the empty seats here? The fire code prohibits people standing near the entrances. Thank you. So our next speaker is Kevin Ellis once more, and this time he's going to tell us about learning to infer graphics programs from hand-drawn images.
Thanks. So vision is very rich. We can infer objects and parts of objects and relations between them, but it's also very abstract. So for example, if you look at a spiral staircase, you can immediately perceive radial symmetry. Or if you look at trees, you see fractal-like structure. Or if you look at mechanical parts like gears, you see a lot of iterated repetition. And there's many, many examples of this. So how could we build machines with similar visual inference abilities? So as a first step toward this, we made a system which looks at a hand drawing and then infers a high-level graphics program describing that image, where that graphics program captures features like symmetries and repeated structures. So we have a two-phase pipeline for going from an image to a graphics program. In the first phase, a convolutional neural network looks at the image and then infers a collection of primitive drawing commands. These are things like circles and rectangles and lines, and they act as a specification or a spec of what the program needs to do. Once we have this specification, we use symbolic program synthesis techniques to infer a program consistent with the spec. And in order to make the search tractable, we also learn a policy that guides the synthesizer. In order to parse an image into primitive drawing commands, we combine two ideas. The first idea from attend, infer, repeat is to decode the objects in the scene one by one, focusing in on them using an attention mechanism, and then rendering them to a canvas on the fly as we decode them. The second idea from neurally guided procedural modeling is to wrap this all up in an outer loop that does sequential Monte Carlo, a stochastic search, over the space of parses of the image. To generalize to real hand drawings, we train it on a synthetic corpus of images that are rendered to make it look like they were drawn by hand. So if you just use the neural network, it does okay as long as you're not evaluating on scenes with way more objects than were in the training data. Here we train on scenes with up to 12 objects, and you really need the sequential Monte Carlo search in order to handle scenes with many more objects than were in the training data. Once we have the specification, we use constraint-based program synthesis to find a minimum cost program consistent with the spec. Here the cost function favors shorter or simpler programs. These programs have things like loops, simple kinds of conditionals, coordinate transformations, and arithmetic. So these synthesizers do a smart kind of exhaustive search, and they always find the exact minimum cost program, but they also can sometimes be very slow. So for our corpus of drawings, on a quarter of all drawings, they take over an hour. In order to make the synthesis be much faster, what we do is we learn a search policy to guide the synthesizer. So what the search policy does is it takes the entire space of all programs and then it chops it up along different axes. So for example, it chops it up into the short and the long programs, or the programs that use reflections and those that don't, or the programs that loop and those that don't. And then it tells the synthesizer how much time it should spend within each of these partitions. So if you don't use the policy, we end up taking around 280 seconds to synthesize a typical program, and then once you do use this learned policy, we can synthesize most programs in about 30 seconds. Here the times are plotted on a log scale, and it's a histogram of the frequencies of different synthesis times. Here are some example programs that we synthesize. In the top, you see affine transformations like rescaling. In the middle, you see reflectional symmetries. And at the bottom, you see a long, complicated program that uses nested loops and conditionals. One reason why you would want to synthesize a program is because it can correct errors made by the neural network. So the idea here is that the synthesizer can favor neural network outputs that lead to shorter or more naturally structured programs. This is a kind of top-down influence of symbolic reasoning at the program level upon the bottom-up perceptual inference being made by the neural network. Programs also support strong kinds of one-shot generalization. So here what we're doing is we're taking a hand drawing, inferring the graphics program, and then generalizing it by extrapolating it. The way that the extrapolation works is by increasing the loop bounds. So we think more generally that this two-phase pipeline is a way that you can integrate bottom-up perceptual inference with top-down programmatic reasoning. For more information, come to our poster on the second floor. Thanks.
Our second oral talk of the day is going to be about learning to reconcile